second to last talk on Rust again. Still staying on the testing theme, so please go ahead.
So good afternoon, everyone. It's 5 p.m. on a Friday, so thank you very much for sticking with me instead of going off to the pub. I'm Andy. I'm going to talk about how we found bugs in the Rust compiler. When you compile code, you would have faith in the compiler that it's going to... you have faith in the compiler that's going to correctly translate your code into equivalent machine code. Unfortunately, compiler authors are also human, and compilers can have bugs like our other software do. Now, ideally, we'd like a piece of software as fundamental as compilers to be fully verified. And there are indeed fully verified compilers for languages like C and ML. But these compilers were purpose-written for static verification. They often sacrifice generated code performance in favor of the ease of verification and are nowhere near as complex as the more industry-adapted compilers. We are still quite far away from being able to fully verify a compiler that wasn't purpose-written. Another approach, which I'm sure you have seen many times today, is fuzzing, also known as randomized testing. Here, we generate a random program, compile it, and see if it runs correctly. And of course, for a complete random program, we don't know what's the right behavior and what's the wrong behavior. So we augment this idea with differential testing, where we compile the same random program using different compilers or different compiler settings and compare the results. We expect them to be the same, but if they're different, then at least one of these compilers have a bug. Using this approach, we developed the first random program generator for the Rust language. We call the generator Rustlantis, that is able to find new miscompilation bugs in the official Rust compiler. And I'll talk about how we did it. So when making a random program generator, the first thing to think about is what to generate. The Rust compiler compiles your source code in stages, broadly divided into the front end and the back end. The front end is responsible for things like parsing, type checking, ownership and borrow checking, and then eventually lowers your code into an intermediate representation called the mid-level IR, or MER for short. Some optimizations are performed on MER to reduce code size and improve performance. This is then lowered into LLVM IR, more optimizations are performed, and machine code gets generated. We are the most interested in these optimization stages because they are the most likely places for correctness bugs to hide. However, if we were to generate just normal Rust code, we call it surface Rust, then we have to confront all these checks in the front end. They are very important, and they are there to uphold all the guarantees, safety guarantees that Rust compiler has, but they have been extensively tested by others, and they do not meaningfully affect these optimizations if we can independently guarantee that the code we pass to the optimizations are valid. Additionally, the Rust compiler, especially at the MER stage, is allowed to transform code in a way that is correct, but would otherwise break the borrow checking rules. So generating surface Rust would actually restrict the diversity of our programs. For these reasons, Rustlantis will not generate surface Rust and will instead produce the mid-level IR directly. Here is a very simple Rust function. It assigns a value to x, increments it in a loop, terminates the loop once x is 10, and returns a number. This is how this function looks like in MER. It is a control flow graph made up of basic blocks. Each basic block can contain 0 or more statements and exactly one terminator, which transfers the control flow from one basic block to another. A terminator can have mutable targets conditioned on the value of a variable, like we see in the match terminator in BB1. This is equivalent to the switch statement in C. One characteristic of MER is that because this is a stage after all the checks in the compiler, all code is unsafe. That means none of Rust's normal safeguards apply. There are no borrow checks, no bounce check, no lifetimes. This is good because it allows us to generate the full range of possible programs, but it also means that our generated code can contain undefined behavior, UB. This function triggers UB by casting a byte that is not valued 0 or 1 to a Boolean typed variable. Breaking the value constraint on the Boolean type. When UB is present, there is no write behavior. The compiler is allowed to do anything. And since we are comparing the result of different compiler settings or different compilers, if our generated code contains UB, we cannot be certain that it represents a miscompilation. For this reason, Rustlantis must prevent UB while maintaining the diversity of the programs that we generate. With that in mind, let's have a look at how Rustlantis is implemented. We generate programs in a top-down fashion. We start with an empty function, declare some local variables, and generate statements to a basic block one at a time. The cursor represents the location of the next statement to be generated. And after a random number of statements are generated, we produce a terminator and then move our cursor into the basic block it targets and continue there. We create a new function whenever we generate a call terminator, move our cursor into there, and start generating basic blocks and statements. We return to the previous function when we produce a return terminator, and the whole program finishes generation when a return terminator is produced in the first function. Note here that Rustlantis' generation flow is in lockstep with a runtime control flow. This allows us to keep track of the runtime state of the program for the purpose of avoiding UB, which may sound restricting, but I'll talk about the solution later on. In this example, you can see that there are variables or fields of variables on both the left and right-hand sides of the program, highlighted in bronze. These expressions are called place expressions. They represent memory locations. Place expressions always start with a local variable and is followed by any number of projections, which can be a tuple or a struct field, an array indexing, or a dereference. We cannot generate place expressions completely randomly. A Boolean variable cannot be indexed, that wouldn't compile. An uninitialized variable cannot be read, that would be UB. A pointer pointing to a deallocated stack cannot be dereferenced, that will be also UB. To keep track of what places we can or cannot generate, we make use of a data structure called the place graph. It records all the reachable places at the current point in the program. Whenever we declare local variables, we add the local variable and all of these fields as nodes to the place graph, with edges in between them representing possible projections. We also keep track of point-to relationships by adding edges whenever a reference or a raw pointer is created, which allows us to know where a reference or a pointer is pointing to at all times. The place graph additionally records the value when a place has been assigned with a literal, and it is interprocedural, allowing pointer-type parameters to be dereferenced in other functions. When we need to generate a statement, we query the place graph to obtain all possible candidates for the current context and pick one at random. When we are in a context where UB is possible, such as division by 0 here, the information in the place graph allows us to generate statements that we know for sure will not cause UB. Besides values, the place graph also helps us in generating programs containing complex control flows. This is desirable because a lot of optimizations are based around loops and branches, which is introduced by the mash terminator. And in this example, let's say that Rustlantis in the place graph knows the value of x would be 4. So the arm with 4 will be the next basic block to generate. But this also means that arms with other values will never be taken. This allows us to add additional branches to a previous basic block, creating a loop structure, knowing that you will not be taken at runtime and thereby having no chance of introducing UB. We can also create what's called decoy blocks, which are populated with the content of a random existing basic block, including the terminator, which could call functions we have already called or visit basic blocks or we have already visited. Since the value of x depends on a parameter, the compiler cannot tell, at least not through intra-procedural analysis, that only one branch will ever be taken. Therefore, it is forced to analyze and optimize this complex control flow, which exposes bugs in the relevant optimization passes. In all of the examples I've shown you so far, there have been references and pointers. And some of you may know that Rust have an extensive set of aliasing rules governing these. Violating any of them would be UB. For example, one of the rules says that if a place has been referenced by a shared reference and you've written to it by whatever mean, then the lifetime of that reference has to end. If you use it again, that is UB. In this code, B is a shared reference to A, and B is invalidated after A has been written with the literal 42. The line in red reading through B causes undefined behavior. To prevent generating code like this, we maintain a borrow stack similar to the one introduced in the stack borrows aliasing model. We keep track of references and row pointers in a stack for each place and add an entry onto the stack whenever we create a row pointer or a reference. Only references and row pointers with corresponding entries on the stack can be dereferenced. So right now we can generate a statement that dereferences both A or B. But if we were to then generate a write by dereferencing A, then everything above A's entry in the stack is invalidated, preventing B from being used later. For the fuzzing harness to tell whether the program behavior has changed from one compilation to another, we print some of the local variables to the standard output. However, even if the program is completely UB-free using the techniques we've talked about so far, we still have one other issue to contend with, which is non-determinism. Some variables are allowed to have different values on each run, such as pointer addresses. So we just can't print pointer type variables. But that's not enough, because non-determinism can leak into values of other types. An integer could be non-deterministic if it was cast from a pointer. A Boolean could also be non-deterministic if it came from comparing the addresses of two pointers. If these values are used in further expressions, then non-determinism would infect the rest of the program, preventing us from being able to tell a compiler bug from normal behavior arising from non-determinism. Globally, therefore, we must exclude some of the operations from being generated, which are pointer to integer casts, pointer comparisons, and floating point to integer transmutations, also known as bit casting in some other languages. This is due to the NaN value being allowed to have non-deterministic bits. Utilizing all of these techniques I've shown you, we've generated a whole bunch of programs and targeted 4 testing backends. Rust with LLVM, which is the default code generation backend, but at different optimization levels. CraneLift, which is an alternative code generation backend to LLVM, and Miri, which is an interpreter that can detect UB at runtime, confirming that our generated code is indeed UB-free. In total, we've discovered 22 unique bugs that were previously unknown. All of them have been reported, and all but one have been fixed. 16 of these are miscompilations, where the user would have no idea that the compiled code is wrong. I'll give you an example of a bug we found in LLVM. So this function checks if something does not equal to the NaN value of double precision floating points. By the standard, NaN does not equal to anything, so this comparison should always be true. When cast to an integer, it should always be 1. But when compiled to x86, it returns 255, which is not even a valid bit pattern for Booleans in LLVM. There are many other bugs, interesting bugs we found. Some of them have been hidden for years, and some of them were serious enough for the patch to be backported into the latest release. And besides the techniques I've shown you, there are other techniques we've used to generate things like structs and pointer arithmetics. And due to time constraints, unfortunately, I cannot show you all. But I hope you can see how Rustlantis is a valuable tool in improving the quality of the Rust compiler. And we are helping Rust to live up to its promise of a safe and performant systems programming language. I strongly encourage you to read the paper, and the source code is available as well. Thank you very much.
Right. Any questions? Can you come up to the microphone so that the video can record it, please? Thank you.
Thank you for the talk. In your the Boolean example, do you know why the assembling code is wrong?
If you dig into the issues, you can probably find out. I can't remember off the top of my head.
Oh, okay.
Yeah. Actually, well, more specifically, there's a parsing LLVM after optimizations called, it converts the IR into a directed acyclic graph and uses that to select instructions on x86. And that, I think that's the part that gets it wrong.
So is it related to the optimization passes, or it's just the code generation?
It's the code generation, yeah. This is specific to x86.
Oh, I see.
Yeah.
Thanks.
Thank you.
Good talk. You said in the beginning that you got to generate intermediate code directly because you're going after bugs in the optimization phase of the compiler.
Yep.
In retrospect, those programs that you did generate and that gave you this list of bugs, could they have been generated from source, or is that just you can see that those programs just absolutely are not really relating to any Rust source code?
So theoretically, from the control flow perspective, all the MER I generated are reducible, meaning that they could be rewritten into normal Rust with like if and for loops and things like that. But I believe there are extra statements that's always added when lowering from surface Rust to MER that could prevent things from being triggered. I cannot tell for certain. I didn't do that experiment or study that extensively.
No, I'm asking because it's if it was possible to get those programs from source, then one could imagine that you could redo your whole research program here and just do Rust source instead, and use the compiler to the level of intermediate and then find bugs there. Maybe.
That would be. I think that would be possible, although I'm not sure about the benefit of doing that, just because we are the most interested in doing the testing the backend stuff, right?
That's fine.
Yeah.
Yep.
Anyone else? Okay. Yep, David.
Thank you for the talk. Very good. One question I have is, you mentioned that it would be hard to generate Rust code due to all of Rust's type checking and constraints and all of that. But then throughout the rest of the talk, you walked through how you were able to generate in the intermediate code that would pass all those type checks or would maintain the same behavior. Maybe I'm just missing something, but what's the gap there? What's the difficulty that makes it harder to generate raw Rust code but not intermediate code?
So I kind of lied a little bit. The MER is not completely typeless. Like, as I said, you can't index a Boolean variable. In the strictest sense, the Rust type system is a linear type system which has ownerships. So moves would be called by the type checker, whereas that's not something that is called at the MER stage. So there are parts of the full Rust type system that gets checked, but some of them isn't. Yeah.
Cool. All right. Thank you. And just to clarify, all of the borrow checking has been done at the high level by the time it gets to...
That's correct. There is no
right.
borrow
So you're
checks here.
completely fully free of all of the lifetime and all of that stuff.
Well, okay. Again, technically, borrow checking is done on MER. But MER has different phases. We do it after the phase we inject the code into the phase that's after borrow check. So there are absolutely no borrow checks at the phase that we inject, yeah.
Okay, cool. Thank you very much.
Thank you.